So, last time, let's discuss what we learned. All right. So, from chapter 8.1, we started with sequences. 8.2, we started with named series. 8.2, we talked about a geometric series, a telescoping series, and the harmonic series. And then as we added on to that, we now have named series called the P series that you were supposed to have memorized. The sum is n goes from 1 to infinity of 1 over n to the p. As long as p is greater than 1, that series is going to converge. If p is less than or equal to 1, the series is going to diverge. Now in terms of tests, the first test we talked about was the divergence test. The second test we talked about was the integral test. The third test we talked about is the direct comparison test. And we just got started on the fourth test that you guys have to memorize, which is the limit comparison test. Okay? So right now we're up to 4 tests, and I'm going to kind of review you guys on the direct comparison test versus the limit comparison test now. But what I'm telling you is this: we got a lot of stuff you got to have memorized. This is the most difficult aspect of chapter 8, is all the different terms and techniques and names of series that you need to have memorized and recognize. And now these are the things you're going to use to prove a different series happens to be converging or diverging. So what I'm thinking about is it's time for us to have a pop quiz in this class, but I think I'm going to give it to you guys on our next class. So you guys will prepare yourself for making sure you know particular name series and what they're supposed to do and some of the aspects on this stuff. So I'm forewarning you now because you need to know this stuff. And it's embarrassing. I sit there and talk to somebody about a geometric series. They have no idea what the formula is and how to actually put a function into a particular series into a geometric series type, so you can tell what it's going to converge or diverge. And if it converges, what does it add up to be? So I'm going to start quizzing you guys on this stuff. Speaking of that, the other thing I also want to remind you guys of, it's still going on. We have our peers, also known as supplement and instruction. So these are free study sessions for you guys. So they're on Monday, Tuesday, Wednesday, and Thursday, paid for by your student fees and stuff. So you should go to these guys and get some help. Great place to get help. And I'm actually taking notes on the people who actually show up to these things and stuff like that. So just remember, this is a great way to study stuff. All right, so let's pick up where we left off. Last time, we were looking on our third test that we have memorized, which is the direct comparison test, the DCT. And it basically stated this, just to remind you guys. You got 2 series, and you're focusing on the sequence part of the series. You got the sequence AN of a series and the sequence BN of a series, where AN is less than or equal to BN. They're both positive, but AN is on bottom, BN's on top. The direct comparison test is if you know one's on bottom and one's on top. So you've got this nice inequality going on here, term to term. If the sum is n goes from 1 to infinity of Bn converges, aka if this series on the top converges, that will automatically imply the series on the bottom will also converge. And vice versa, if you notice that the sum is n goes from 1 to infinity of An, which is your series on the bottom, if it diverges, that will automatically force the guy on the top. The sum is n goes from 1 to infinity of Bn to also diverge. But the inequality is very important. When the guy on the top as a series converges, the guy on the bottom must converge. If the guy on the bottom as a series diverges, the guy on the top converges. What does it say about the guy on the top that diverges? What does it say about the guy below him? Absolutely nothing. If the guy on the bottom is converging, what does it say about the guy above him? Absolutely nothing. You've got to get the inequalities just right. The guy on the top has to converge, forces the guy on the bottom to converge. If the guy on the bottom diverges, it forces the guy on the top to diverge. So you've got to get the inequality just right. And we did several of those problems on setting up these inequalities. But what if you can't get that inequality just right? You know, adding 1 to the denominator makes the denominator bigger, but makes the overall fraction smaller. But I think the guy on the bottom is going to diverge. Then the direct comparison test is not going to help you out at all. So we came up with And this is the probably the more heavier weight problem that we use, and that is the limit comparison test. And I told you guys last time, if I'm going to do a comparison test, probably about 90% of the time I'm going to do a limit comparison test, because it's a pain to get these inequalities just right. I mean, I got to really notice, oh, look, this guy's smaller than this guy. And that's just a rare thing for you guys to notice, and rare that it actually works perfectly and stuff. What happens when the guy on the top versus the guy on the bottom? They're very, very close, but the guy on the top is actually divergent, and I can't get the guy on the bottom to be the inequality. It's just wrong. Well, then try a limit comparison test. And it says this. You got two series, AN and BN. Now, and I mentioned this before. The way I'm coding this stuff, AN, the sum is n goes from 1 to infinity of AN, is the unknown series. The sum is n goes from 1 to infinity of BN is the known series, and they're both positive term series. And if you take the limit as n approaches infinity of the ratio of the unknown sequence over the known sequence of these series, and you get a number, a constant, which is not 0 and it's not infinity. It's got to be finite, but it can't be 0. If you get a number out of these two guys, then both series will do the same thing. And since the known one it converged, that will force the unknown to converge. If the known one diverged, it will actually force the unknown to diverge. They're going to do the same thing, either converge or diverge. Okay? And so I did this particular problem for you guys last time. And the trick on these limit comparison tests, and I call this the mental comparison test, is look at this guy. This was the sum as n goes 1 to infinity of n squared plus 2n minus 5 over n to the 4th plus n plus 7. When you're looking at these classic series of polynomials over polynomials, the guy that's in charge is the degree term, the classic polynomials. So in terms of the term that's in charge, I got n squared plus 2n minus 5. The degree term comes from that n squared. And for the denominator, it's n to the 4th. So I just focus on that. So and I put this little squiggly equal to, because you won't get the less than greater than. That would be a direct comparison test. It's got to be comparable. This is going to be the sum as n goes from 1 to infinity of n squared over n to the 4th, which reduces down to 1 over n squared when you clean it up. This is a P series. We have it memorized. P equals 2, which is bigger than 1. This series converges. This is the guy we're going to compare to. And so to prove the math, I'm going to do the limit comparison test. I'm going to take the limit as n approaches infinity of the ratio of the unknown sequence of my series divided by the known sequence of the series, and I'm going to clean it up, and then I'm going to take my limit as n approaches infinity. And as I mentioned to you last time, if you do this right, your degree of the top and degree of the bottom are going to end up being the same. And after you clean it up, and then you get the limit of the limit as n approaches infinity ends up being the ratio of the leading coefficients. You don't have to do L'Hopital's rule 14 times to be able to get the answer. You should be able to just look at it and tell what the answer is. And since this is your C value, C equals 1, and since 1 is not 0 and it's not infinity, this tells me by the limit comparison test that this unknown series, should be the unknown series, and the known series are going to do the same thing. This was a P series, P equals 2, converge. That forces this guy to converge by the limit comparison test. Stating my proof. This next one is a problem that is unusual, but it actually works. It's the sum as n goes from 1 to infinity of the sine of 1 over n. I'm throwing a trig function at you guys. Yeah, throwing a trig function at you. But if you look at this trig function, you should notice something rather. This is sum as n goes from 1 to infinity of the sine of 1 over n. The thing that just stares at in your face is that 1 over n. Because the hardest part about any comparison test is, what are you going to compare it to? Well, I'm going to compare this one to, and I'm going to do this little squiggly equal to, the sum as n goes from 1 to infinity of 1 over n. Now, I see that 1 over n, so this is the guy I want to compare it to. This is my known series. Now, you got to tell me about your known series. What's the sum as n goes from 1 to infinity of 1 over n? What's this dude's name? Speak loud. You should know it. Otherwise, you could take this class again. Harmonic what? Series. And what does the harmonic series do? Diverges. Thank you for those two people that know this. Otherwise, you guys are not going to do real well on my pop quiz on Friday. You need to know this stuff. It's pure memorization. This is the harmonic series. It diverges. Does that make sense? So, now I'm doing the limit comparison test. So I'm going to set up my limit for the limit comparison test. So here's my LCT, the limit comparison test. I'm going to take the limit as n approaches infinity of the ratio of the unknown series sequence part. The sequence of the unknown is the sine of 1 over n, divided by the sequence part of the known series, which is 1 over n. Now, I'm going to do this because I think some of you guys forgot all that stuff you learned in Calculus 1. So first rule of limits is plug it in. I'm going to show you what I'm going to get. When I plug this thing in, this will be the sine of 1 over infinity divided by 1 over infinity. But what is 1 over infinity, also known as 0? So this is the sine of 0 divided by 0. What is the sine of 0? Thanks to trig in high school, we learned this stuff. The sine of 0 is 0 over 0. So for me to be able to do this limit, I got to use L'Hopital's rule. This one you actually have to show me the L'Hopital's rule on. So L apostrophe H, L'Hopital's rule. This will be equal to the limit as n approaches infinity of the derivative of the numerator over the derivative of the denominator. Well, this is the sine of 1 over n. So what's derivative sine? Chain rule. Derivative sine is cosine. Inside stays the same, 1 over n, times the derivative of the inside. What's derivative of 1 over n? Well, 1 over n is the same thing as n to the negative 1. So what's the derivative of that? Negative 1 n to the negative 2. Does that make sense? Divided by the derivative of 1 over n. Well, 1 over n is n to the negative 1, and that gives you negative 1 n to the negative 2. Remember your L'Hopital's rule. You take the derivative of the numerator, divide by the derivative of the denominator, and then you redo your limit. But before you do the limit, clean it up. Something cancels here. Clean up that canceling. What cancels? The negative 1 n to the negative 2 cancels with the negative 1 n to the negative 2. This leaves you with the limit as n approaches infinity of the cosine of 1 over n. Now, plug in your infinity. This will be the cosine of 1 over infinity. But 1 over infinity is 0, and the cosine of 0 is what? 1. So therefore, C is equal to 1 in terms of the limit comparison test. Therefore, since your C is equal to 1, not 0, not infinity, and thus the sum as n goes from 1 to infinity of the sine of 1 over n is what? Well, what did we compare to? We compared the sine of 1 over n, the sum as n goes from 1 to infinity of the sine of 1 over n, to the sum of 1 over n. And the sum of 1 over n is the harmonic series, which does what? Diverges. And since I got a limit of a constant, C value is a constant, they're going to do the same thing. So the sum as n goes from 1 to infinity, the sine of 1 over n is divergent by the limit comparison test. And there's my statement of proof of why this guy is going to diverge. Does that make sense? Questions? Notice how I'm writing this stuff up. So again, at this point is where I need to remind you guys of how are you going to do so well on this test? The first thing you're going to do is you're going to have to start studying and memorizing stuff. I know, it's the end of the semester, I'm tired. Don't care. It's college. Get used to it. So, you got to first off study. And the best way to study this stuff, honestly, is the way we used to study when we were in kindergarten, first and second grade, learning multiplication tables. Flashcards. Drill, drill, drill. First thing you need to do on your flashcard is write down the test. This is the limit comparison test. You need to know what the limit comparison test states. And then, right underneath the limit comparison test, you need to write yourself out a complete and total example of this test being worked out. Write up this thing right here so you can work the process. Because every problem that I'm going to give you that requires the limit comparison test, I'm doing the same process over and over again. You need to see this process and actually take an example and memorize how that process went. So when I change the numbers on you and change the function, you can still do the process. And that's for the direct comparison test, limit comparison test, the divergence test, the integral test, every test I give you. You need to write out exactly and memorize what the test actually states, and then write out underneath that an example of this test in use. And once you catch the pattern, you can do any problem that I give you guys on the test and or the departmental final exam. All right, so let's take a look at this guy. I got the sum as n goes from 2 to infinity of 1 over n cubed minus n. Okay? If I was going to do this problem, I'm going to do a comparison test. Anytime it's a 1 over n cubed minus n, I'm going to, it's polynomial or polynomial, I'm going to do it like a comparison test. The problem is, well, can I do the direct comparison test or limit comparison test or whatever? I always do the limit comparison test unless it's something special. Like, for example, that last one with the sign, that one may be a little more difficult to do a direct comparison test unless you know that the sine of an angle is always less than the angle or something like that. Then you can do it. Getting inequalities on trig, for most folks, is difficult. So, this one, I'm going to do a limit comparison test, squiggly equal to. The question is, what are you going to compare to? I'm going to compare to the sum as n goes from 2 to infinity. Always use the same summation. But remember, the degree term is the guy that's in charge. I don't care about the rest of them. What is this guy? It is 1 over n cubed, because of that n cubed degree term right there. Does that make sense? The minus n doesn't matter. Okay? Now, what's the series? What's its name? You have to tell me. This is a p series. P equals 3, which is bigger than 1, which means this series does what? Converges. P series, P equals 3, greater than 1, converges. Short, simple sentences. We're math people. Don't have to be too elaborate on your sentences. There it is. It's a convergent series. Now I actually have to show you the use of the limit comparison test. I'm going to take the limit as n approaches infinity of the ratio of the sequence part of the unknown series, which is 1 over n cubed minus n, divided by the ratio of the sequence part of the known series, which is 1 over n cubed. I'm going to clean it up by invert and multiply. This gives me the limit as n approaches infinity of n cubed over n cubed minus n. And what is the limit as n approaches infinity of n cubed over n cubed minus n? You could do L'Hopital's rule a couple of times if you want to, but if you notice the fact the degree of the top equals the degree of the bottom, the answer is the ratio of leading coefficient. What's it going to be in this example? 1 over 1, which is equal to 1. Therefore, your C equals 1. Okay? That tells me that these two series are going to do the same thing. Therefore, the sum as n goes from 2 to infinity of 1 over n cubed minus n is convergent by the limit comparison test. There's my proof. I had to show you that the limit of the known series that I compared to, known sequence of the sequence part of the known series that I compared to the known sequence of the sequence of the unknown series, that limit gives me a number. In this case, it's 1. That's not 0, not infinity, and that means it's going to be they're going to do the same thing. Now, question for you: could I have used the direct comparison test on this problem? Yes or no? Well, the difference between these two guys, to do the direct comparison test, you've got to get that inequality just right. This series converges. But let's take a look at how these two series line up. When you subtract n from the denominator gets smaller, so the overall fraction gets what? Bigger. So this is actually greater than this guy right here. This series converges. And this series, the sum of n goes from 2 to infinity of 1 over n cubed minus n, is actually bigger than the known series that converges. What does it tell me about this series? Absolutely nothing. The guy on the bottom converges. What does it say about the guy on the top? Nothing. The only way a direct comparison test works is if the guy on the top converges, then anybody below him converges. But this guy's not below him. He's bigger than him. So I could not have used the direct comparison test on this guy. It would only be the limit comparison test. But the limit comparison test says, yeah, they're going to converge. Okay? What about this guy here? This one. Here's the deal. There's certain problems out there that you don't want to use the limit comparison test on. For the most part, I don't want to use one that actually uses trig functions. Why? What is the limit as n approaches infinity of the sine of theta, or sine of n? What's the limit as n approaches infinity of the sine of n? Well, it's a sine wave. It bounces what? Somewhere between -1 and 1. It doesn't converge to anything. So when you're doing limits, you want to avoid limits of trig functions. There was that very special problem that I did, which was this guy right here, and that's only because of the beautiful L'Hopital rule that the angle and the series that I was actually going to compare to were the same thing. The sine of 1 over n, and then the sum of 1 over n. So this one worked out very special. So you see this problem right here? This is one I do not want to use the limit comparison test to. Because one, who are you going to compare to? And number two, when you take your limit, your problem is going to be, honestly, the limit of taking limit as n approaching infinity of the sine squared of n. That's going to bounce somewhere between 0 and 1, and it doesn't converge. So I'm not going to get an actual C number out of this guy, so I can't use the limit comparison test. This one actually, just to try to show you the difference, this one could not use direct comparison test. This one could not use limit comparison test. It's the trig on this guy that's killing me. But as I just mentioned a few seconds ago, this one is one that I'm actually going to use the direct comparison test. So I'm trying to give you an example of why both tests. Well, 90% of the time you're going to use the limit comparison test. There's this 10% of the time that I'm going to have to use the direct comparison test where the limit comparison test won't work. Here's the deal. We know that the sine of n for any n bounces between -1 and 1, right? So to make them positive, you square it. Well, how does the sine squared of n, how does that compare? It bounces between what two numbers? 0 and 1, right? When you square sine, you bounces a number between 0 and 1. And it's bounded by 1. So here comes my direct comparison test. So therefore, the sum as n goes from 1 to infinity of the sine squared of n over n times the square root of n would actually be less than or equal to the sum as n goes from 1 to infinity of 1 over n times the square root of n. Right? I replace the sine with what it gets at most, its maximum, which is at 1. Right there. I replace sine with 1, so it's the inequality less than or equal to, but my denominator is the same. Let's clean up that denominator. This is the sum as n goes from 1 to infinity of 1 over n. Square root of n is times n to the 1/2. Clean it up. What's n times n to the half? When you multiply, what do you do with the exponents? You add. So what do you get? The sum as n goes from 1 to infinity of 1 over n to the 3/2. Does that make sense? What's this series name? P series. What does P equal to? 3/2. Never said P had to be an integer. P can be all kinds of numbers. Fractions, rational numbers, whatever. But how does 3/2 compare? 3/2 is what? Greater than 1, which means this series is going to converge. So it's convergent. This is a convergent P series. Convergent P series. Therefore, understand, the guy on the top converged. What does that force the guy below him to do, according to the direct comparison test? It converges. Therefore, the sum as n goes from 1 to infinity of the sine squared of n over n times the square root of n is convergent by the limit comparison test. Oh, wait a minute, wrong one. Direct comparison test, sorry about that. The direct comparison test. That's the one we're actually using. I could not use the limit comparison test. This is the direct comparison test. So here is a great example of where you would have to use the direct comparison test. I can compare it to something on top by getting rid, notice I got rid of the trig. Sines and cosines are bounded by 1. Now remember, to do the limit or direct comparison test, the terms have to be positive. The sequence has to be positive. So you notice they squared the trig function. That makes it positive terms. And sine and cosine squared are both less than or equal to 1. So when I see a trig in a series, for the most part, I'm going to use the direct comparison test because I can bound that trig and get rid of the trig, and then I can just focus on the rest of the sequence part. And that's what I did in this example. Does that make sense? Another great problem to study. But again, if you look at these two problems here, this one, I set you up, but I could not have used the direct comparison test because Well, added 3 to the denominator makes the denominator smaller, makes the overall fraction bigger. The inequality would have gone in the wrong direction. But this is a great example of how the power of the limit comparison test. So you don't have to worry about less than or greater than. As long as you got some guy that's really close to compare to, and you take your limit and you get a constant out of it, then the series are going to do the same thing. But sometimes you can't take that limit, especially when it comes to interesting functions like trig, because they don't converge. The limit is n approaching infinity of sine squared of n. It bounces between 0 and 1 and doesn't converge, so you won't get a c out of this guy. But I could do the direct comparison test by the sine squared is always bounded above by 1, and then that when the rest of it turns into a p-series, and since the p-series converge, anybody below him is going to converge by the direct comparison test. Take a look at some of your web work problems. All right, here is web work. So enjoy. I try to pull some of those off that give students problems before you guys. It says this, quote, each of the following statements is an attempt to show that a given series is convergent or divergent. For each statement, enter C if it is correct, if the argument is valid, enter I for incorrect, so C or I, okay? Or any part of the argument is flawed, any part of it. Note, the conclusion is true, but the argument that led to it is wrong. You must enter I. So you look at this problem, so great, I'm going to sit there and do probabilities here. I'll type in C, 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 and then it'll tell me which ones are wrong, and then I'll go back and change it to I. No, you only got one shot at these guys. Okay? We got you out thought. We know what you people do. It's pretty sad. So, one shot. Is this correct or incorrect? So here we go. So, for n greater than 2, 1 over n times the natural log of n is less than 1 over n. Is that true or false? Well, I multiply by the natural log of n to n in the denominator, which when the natural log of n, when you start getting bigger than 2, natural log of 3, 4, is going to be a number bigger than 1. So you're multiplying by a large number, makes the denominator bigger, but makes the overall fraction what? Smaller. So this inequality is good to go. And does the series 1 over n diverge? It do. That's called the harmonic series. We have that one memorized. So, therefore, by the comparison test, and it's the comparison test, Weber calls the comparison test. This is actually the direct comparison test. The series is divergent. True or false? What's wrong about it? The guy on top diverged. When the guy on top diverges, what does that say about the guy below him? Nothing. This is an I. It's great. You're comparing it to divergent, but the inequality is wrong for the sense of trying to compare it to a divergent series on the direct comparison test. So that would be an I. All right? Take a look at the next guy. For n is greater than 3, 1 over n squared minus 4 is less than 1 over n squared. True or false? You subtracted 4 from the denominator, makes the denominator smaller, makes the overall fraction what? What? Bigger. Well, that's just wrong right there. You subtracted 4 from the n squared, makes the bottom smaller, but makes the overall fraction bigger. Inequality is wrong. I don't care about the rest of it. It's false. Yes, it's true that 1 over n squared, sum of 1 over n squared, p series p equals 2, it converges. And therefore, this thing converges. It's true, this thing really does converge, but I don't care. Their argument is flawed because they had the inequality wrong way. Does that make sense? This is what you're looking for. Look at the next one, number 3. For n is greater than 1, 1 over n squared plus n plus 4 is less than 1 over n squared. Well, let's check it out. To the n squared, we're adding an n and we're adding 4. We're adding stuff to the denominator. Makes the denominator bigger, makes the overall fraction what? Smaller. So that is less than. That's good. And the series, the sum of 1 over n squared, converges. That's true. This is a p series, p equals 2. So by the comparison test, the series, the sum of 1 over n squared plus n plus 4 converges. That's true. The guy on top converges, forces anybody below him to converge. This is a correct statement. This is direct comparison test. The guy on the top converges, anybody below him converges. When I'm comparing it to a divergent, the guy that diverges must be on the bottom to force anybody above him to diverge. That's direct comparison test. Here's another interesting way WebWorker is going to ask you questions on this section. It says this: list the first correct reason. See, here's your problem. when it comes to these tests, you've got a lot of tests. You've got a lot of tests. And there may be more than one test to prove something is going to converge or diverge. There's only one answer. It converges, it's going to converge. There's only one answer. It's going to diverge, it's going to diverge. Okay, but there may be more than one test. Maybe you could have used a comparison test. Maybe you could have integrated the darn thing and used an integral test. There's lots of different tests you could possibly use, but there's only one answer. So because of that, they got these things lined up. Is this a divergent p-series? Is it a divergent geometric series? Or you can compare with a divergent p-series if it's not completely a p-series. Maybe compare it to a p-series. Diverges because the terms don't have a limit of 0. That's called the divergence test. Or maybe you could have used the integral test to actually prove this thing is going to diverge. So all these things are going to diverge. You're given the series diverges. So you don't actually have to test anything. The question is, which is the first test? They got them in order. Is it a divergent p-series? If it fails that, then go down to divergent geometric series. If it fails that, compare with the divergent p-series. If it fails that, maybe the terms don't have a limit of 0. If it doesn't have that, maybe the rest of them are all wrong, but you could have integrated it, and then you would use the integral test. That would have been your answer. So take a look at this guy. Is this a actual p-series? Sum of 1 over n to the p? No, it's not. So A's off. Is it a geometric series? Geometric series is nothing but a sum of a number raised to the power of n. You got numbers raised to the power of n on this thing? Nope, it is not a geometric series. So B's out. Would you compare to a divergent p-series? Well, again, the problem is when you multiply by natural log of n, when n's bigger than greater than 3 or better, it makes the denominator bigger, right? When you multiply it, that makes the overall fraction smaller. So you could compare to 1 over n, but here's your problem. 1 over n does what? Diverge. So you really can't compare it to diverge because the only way to get something out of comparing to a diverge, it's got to be greater. This is smaller. So that's it. When you take your limit, so you can't really compare it to a divergent p-series, do the terms have a limit of 0? When you take the limit of the sequence part, does it get 0? What's 1 over infinity times natural log of infinity? Natural log of infinity is infinity times another infinity is infinity. 1 over infinity is 0. Yep, they have 0. So could you integrate this guy if you put a gun to your head and said integrate it? Could you do it? Yeah. What technique would you use to integrate this guy? If it's the integral of 1 over x natural log of x dx, what would you use? Use substitution. What would you let u equal to? Natural log of x, what's derivative? 1 over x, which is also in the problem. You could integrate it. So the only answer on this lineup here is E. The rest of them actually failed. E is the only one that actually works. Does that make sense? You could integrate the guy. Try about this guy. I could also integrate this one. Wait, you got to do it in order. Is this a divergent p-series? Nope. P is 1 over n to the p. Nope, that's not it. Is it a geometric series? Nope, it's not n to a power. It's going to be a number raised to a power of n. It's not that, so it's not a geometric series. Could you compare to a p-series? Yeah, you actually could, because this time the natural log of n is in the numerator and not the denominator. So the natural log of n is going to get bigger and bigger and bigger, which will be greater than the sum as n goes from 3 to infinity of 1 over n. This is the harmonic series, but officially he's a p-series, p equals 1. This thing does what? It's a harmonic series. What does the harmonic series do? Diverge. And this guy is bigger than diverge. What's this guy going to do? Diverge. We compared it to a p-series, so the answer for this one is C. Does that make sense? This one. Is this a p-series? Nope. Is this a geometric series? Nope. Is this could you compare to a divergent p-series? Well, this thing's natural log of n, so it's not a polynomial, so you're not going to compare to a p-series. Do the terms have a limit of 0? Actually, this would be the divergence test. Notice your sequence part. It's natural log of n. When you take the limit as n approaches infinity of the natural log of n, you get the natural log of infinity. But we know from calculus 1, the natural log of infinity is infinity. These things don't get smaller, they get bigger. So you're getting numbers that are bigger and bigger and bigger. And when you add that up, it's going to blow up to you very quickly. This is divergent by the divergence test. It diverges by the divergence test, which means it's actually D in your lineup. The terms don't have a limit of 0, therefore automatically the series is going to diverge. And what about this last guy? Sum as n goes from 3 to infinity of 1 over n. What's that dude's name? harmonic series. And what does the harmonic series do? It diverges. So we know it diverges, but harmonic series is P series, P equals 1. So this is a P series, even though we gave it a special name, harmonic series. P equals 1, so the answer for this one is A. Does that make sense? All right. Section 8.4. You'll notice that all the series that we've done up to date had to be quote-unquote positive term series. When we did the direct comparison test and the limit comparison test and the integral test, they all had to be positive term series. All the terms had to be positive, decreasing, and continuous for the integral test. Does that make sense? What if they're not? Well, the next type of series we're going to look at, and we got a whole section on this called alternating series test. You remember us when we were talking about sequences, we threw in this concept of -1 to the n. And when you throw in -1 to the n, it gives you +1, -1, +1, -1, depending on the power of n, when it's even versus odd. -1 to an even power is 1, -1 to an odd power is -1. So you get plus or minus the whole way down. So, just to let you guys know, we're talking about an alternating series. So, hopefully you watched the awesome pre-section video on this stuff. But with alternating series, we're talking about two different kinds of, two series here. I want two different looks. It's the limit is the sum as n goes from 1 to infinity of -1 to the n times an. Okay? This is an alternating series. And I think in our book, we call this bn. The whole thing's called an, but this is the sequence part. But you notice you got this -1 to the n. That -1 to the n makes it an alternating series. So it could be -1 to the n, -1 to the n plus 1, -1 to the n minus 1. It's -1 to some power of n. That makes it an alternating series. Does that make sense? But sometimes they try to be fancy with you guys. There's also this look. The sum as n goes from 1 to infinity of the cosine of n pi times bn. What's the cosine of n pi? Well, remember, n goes 1, 2, 3, 4. Plug it in. What's cosine of pi? -1. What's cosine of 2 pi? 1. What's cosine of 3 pi? -1. Cosine of 4 pi? 1. So this is a fancy way of making a series alternating. The obvious one is -1 to the n, so you're kind of focused on -1 to the n, it's alternating series. But when you see cosine of n pi, yeah, that's alternating series too. It's just written in the fancy way of writing it out. So this is the kind of series that we're talking about. So hopefully you watched the awesome pre-section video and took notes on these examples. Okay? So, in terms of the algebra review on this particular section here, just to remind you of some stuff. Increasing, decreasing test. How do you tell if a function is increasing or decreasing? That's back to calculus 1 at its best. You take the derivative of it, and if the derivative is positive, it goes up, it's increasing. When the first derivative is negative, it goes down, it's decreasing. So, if the first derivative is greater than 0 on an interval, f of x is increasing on that interval, and f prime of x is less than 0, if the derivative is negative on an interval, then f of x is going to be decreasing on that interval. So this is, again, back to calculus 1 at its best. Find an interval of increasing and decreasing for the function of f of x equals 3x squared plus 18x. First thing you want to do is take derivative of it. Derivative of 3x squared is 6x, plus derivative of 18x is 18. You're first going to find your critical values by setting it equal to 0. So 6x equals -18, divided by 6, x equals -3. This is your critical value. But for intervals of increase and decrease, we taught you guys, anytime you hear the word intervals, draw a number line. So I'm going to draw a number line and label it. This is the first derivative number line for increase, decrease. It was a second derivative number line for concavity. So we put our critical value up here of -3, and I'm going to do some test values. I'm going to pick a number less than -3. I choose -4. I plug into my derivative. That'll be 6 times -4 plus 18. -24 plus 18 equals -6. I don't care what the number is, it's negative. And pick a number bigger than 3. Use your brain. I choose 0. Plugging in 0, 6 times 0 plus 18 equals 18. Don't care what the number is, it's positive, so everybody in that interval is positive. So to answer the question, from negative infinity to negative 3, it is decreasing, and from negative 3 to infinity, it is increasing. They did ask for increasing, so the intervals of increasing is from negative 3 to infinity. A little calculus 1 action here, just to help you out. So, you look at this guy. Does the sequence, because that's what we're really into here, does the sequence an equals 3n plus 3 divided by 2n squared increase or decrease on the interval between 0 and infinity? Okay, so again, an is going to be this 3n plus 3 over 2n squared. So, if I want to figure out what interval this thing is going to be increasing and decreasing on, you do this. I'm going to call him f of x just to make him look good. 3x plus 3 over 2x squared. I'm going to take the derivative of this guy. What rule would I use to take derivative of 3x plus 3 over 2x squared? Quotient rule, derivative of the top times the bottom minus the top times derivative of the bottom all over the bottom squared. So derivative of the top is 3 times the bottom, 2x squared, minus the top, 3x plus 3, notice the wonderful use of parentheses there, times derivative of the bottom, 4x, all over the bottom, 2x squared squared. Cleaning them up, this is 6x squared minus, and I'm going to distribute the negative and distribute the 4x at the same time, minus 4 times 4x times 3x is going to be what, 12x squared, minus 12x all over 4x to the fourth. Cleaning it up, f prime of x is equal to negative 6x squared minus 12x over 4x to the fourth. That is my first derivative. You'll notice something or other. There's a point that the first derivative does not exist at. F prime of x does not exist, d&e's, at x equals 0. So we're going to have to omit x equals 0. But we're looking for critical points. So, to find critical points, I'm going to set my derivative equal to 0 and solve. I'm going to multiply both sides by x to the fourth. This part will cancel. I'm left with negative 6x squared minus 12x equals 0 times 4x to the fourth is 0. Factoring out a negative 6x, I'm left with x plus 2 equals 0. You with me? And then set each factor equal to 0 and solve. I get x equals 0 and x equals negative 2. To find intervals of increase and decrease, I'm going to draw my number line. It is a first derivative number line. But I got 0, but 0 doesn't exist, so I got to put 0 on this thing with an open circle on him. And then I'm going to also put negative 2 as my other critical point. I'm going to do test values around this guy. So I'm going to plug in f prime of negative 3. A number between negative 3 and 0, I choose negative 1. And then a number bigger than 0, I choose 1. I'm going to plug all these numbers, negative 3, negative 1, and positive 1, into my derivative. Grabbing my handy-dandy calculator here. Plugging in negative 3. Negative 3 squared is 9. Negative 6 times 9 minus 12 times negative 3 is going to be negative 18 divided by negative 3 to the fourth is 81, and 81 times 4 is 324. I don't care what the number is. What's the sign of it? It's negative, so I'm decreasing in that interval. When I plug in negative 1 into my first derivative, I get negative 1 squared, which is 1. That'll be negative 6 times 1 minus 12 times negative 1 divided by, and that would be 6, divided by negative 1 to the fourth is 1 times 4 is 4. I get 6 fourths, 3 halves. Who cares? It's positive, so it's increasing in that interval. Now plug in 1. 1 squared is 1. Negative 6 times 1 is negative 6. 12 times 1 is 12. 6 minus 12 is minus 18. Over 1 to the fourth is 1 times 4 is 4. Negative 18 divided by 4 is negative. So it's negative in that interval. So the question is, quote, does the sequence AN increase or decrease on the interval between 0 and infinity? All we care about is between 0 and infinity. And 0 into infinity, from 0 to infinity, the AEN, which is your function, is decreasing. Reminding you of the use of calculus 1. Does that make sense? Just practicing here. All right. Now, here's the big deal. All right, what number test we up to? Number 5. This is called an alternating series, and this test is called the alternating series test. We're math people. What are we going to call it? You got it. AST. The alternating series test. Here's the deal about an alternating series. It's very direct. You have an alternating series. The sum is n goes from 1 to infinity of -1 to the n, or n plus 1, or n minus 1, times bn. And so when you write this out, you get something like b1 minus b2 plus b3 minus b4. It's alternating. It's an alternating series. Here's what you have to do. You got to check two things. First thing you got to do is you got to make sure the terms go down, and it's the bn. So drop the alternating part and focus on just the bn. Do the bn's go down? Does the bn plus 1 less than or equal to bn for all n? You got to make sure the terms go down, and you can write out the terms and see if they're going to go down. And if worse comes to worse, you're not sure, take the derivative of it and see if it's going to be decreasing. But typically we just write out some terms you can see that are going to be going down. But most important is number 2. You got to take the limit as n approaches infinity of the bn, the sequence part without the alternation, and you got to get 0. Two things. The terms have to be going down, and the limit of the sequence part without the alternation has got to go to 0. And if these two things hold, the terms decrease and the limit goes to 0, then the alternating series is going to converge. If you don't get a limit of 0 and the terms don't go down, then it's going to diverge. It's one or the other. The terms have to decrease and the limit has to go to 0. It's going to converge. So let's take a look at this guy. I got the sum as n goes from 1 to infinity of -1 to the n plus 1 divided by n. It's not the harmonic series because it's alternating. I got -1 to the n plus 1. What this guy really is equal to, when you plug n equals 1, n equals 2, n equals 3, n equals 4, you get 1 plus 1, which is 2, -1 squared is 1 over 1. And then you plug in 2. 2 plus 1 is 3, -1 to the third is -1, minus 1 over 2. And then you get plus 1 over 3, minus 1 over 4, plus 1 over 5, minus ... It's an alternating series. So we're going to check it. The bn, the part without the alternation of the sequence part of your series, is 1 over n. Drop the -1 to the n part. The rest of it is 1 over n. We're going to check two things. Number 1, the bn equals 1 over n. Does it go down? Well, plug in some numbers. N equals 1, n equals 2, n equals 3. This is 1 over 1, which is 1, 1 over 2, 1 over 3. What's happening to my numbers? 1 over 3, 1 over 4. They are going down. Check. Number 2, the limit as n approaches infinity of bn. This will be the limit as n approaches infinity of 1 over n. What's the limit as n approaches infinity of 1 over n? 1 over infinity, which is what? 0. Check. The terms decrease and the limit goes to 0. Therefore, the sum as n goes from 1 to infinity of -1 to the n plus 1 over n is convergent by the alternating series test. This is not the harmonic series. Harmonic series diverges, but once you put that -1 to the n stuff on it, it actually makes it into a convergent series. And you prove that by the alternating series test. And this is how you write it up. So there's going to be a lot more tests for us to use, but we'll do those next time. So get used to the alternating series test. That is going to be our number 5 test. And don't forget, quiz on Friday. See if you guys have this stuff memorized. See you guys then.